Good morning, everyone. Today, we were discussing the topic of status of matter for A-level student. In this part 1 session, we will cover several important formula related to gases, including Bohr law, Charles law, and ideal gas law. Additionally, we will look at some exam questions and provide summary of the liquid states. Without further ado, let's get started. State of matter gases. All substances exist in one of three states of matter: solid, liquid, or gas. Gases are different from solid and liquids because they have neither a fixed shape nor a fixed volume. This is because the particles in a gas are far apart and move freely, bouncing around and spreading out to fill whatever container they are in. When gas particles collide with each other or with the walls of the container, they exert pressure. According to Bohr law, P multiplied by V equals constant. This law says that if the temperature is constant, the pressure of a gas increases when its volume decreases, and vice versa. In simple terms, if you squeeze a gas, reduce its volume, the gas particle collide with the wall more often, increasing pressure. If you give the gas more space, increase its volume, the collision becomes less frequent and pressure decreases. According to Charles' law, V divide T equals constant. This law states that when the pressure is constant, the volume of a gas increases as its temperature increases. In other words, when a gas is heated, the particle move faster and spread out more, causing the gas to take up more space. If the gas cools down, the particle move slower and the gas shrink. According to ideal gas law, PV equals nRT. This equation relates pressure P, volume V, and temperature T of a gas with a number of particles N and the gas constant R. It shows how all these factors are connected. For example, if you increase the temperature of a gas, its volume will increase if the pressure stays the same. In all this law, the idea is that gas particles are constantly in motion and their interactions with the container and each other change the gas pressure, volume, and temperature. Questions. In an experiment, 0.217 G of liquid was vaporized in a shrink places in an oven at 80 Celsius and 101,000 Pascal pressure. The vaporized liquid gave 66 centimeter cube of gas. Calculate the relative molecular mass of the liquid. So to answer to this question, to calculate the relative molecular mass of the liquid, we can use the ideal gas law. The ideal gas law is expressed as PV equals nRT, where P is a pressure in Pascal, V is a volume in cubic meters, N is the number of moles, R is the ideal gas constant, which is 8.314 joules, and T is a temperature in Kelvin. First step is you have to convert the unit. Convert the volume from centimeter cube to meter cube. Based on the question above, V equals to 66 centimeter cube. So we have to convert the unit and it becomes 6.6 multiply 10 to the power of -5 meter cube. Then convert the temperature from Celsius to Kelvin, where T equals to 80 Celsius plus 273.15, get the value 353.15 Kelvin. Step 2, substitute value into the ideal gas equations. Given P equals to 101,000 pressure in Pascal, R equals to 8.314 joules, and T equals to 353.15 Kelvin, V equals to 6.6 times 10 to the power of -5 meter cube. Substitute this value into the ideal gas law. where you get 101,000 in Pascal times 6.6 times 10 to the power of negative 5 equals n times 8.314 times 353.15. Step 3, solve for n number of moles. N equals to 101,000 in Pascal times 6.6 times 10 to the power of negative 5 divided by 8.314 times 353.15, you get the value approximately to 0.00227 mole. Step 4, calculate the relative molecular mass, where using the formula M equals to mass divided by N, where the mass of the liquid is 0.21 g or 0.000217 kg. M equals to 0.217 g divided by 0.00227 mole, you get the value of molecular mass of the liquid, approximately 95.7 grams per mole. The liquid states. Melting. This is the terms given to the change of the solid into a liquid. If you think about the bond between the particles in solid, this bond needs to be broken in order for the solid to melt. In other words, energy must be supplied. So this particle separate but do not move very far apart. So the energy required depends on the strength of the original bond in the solid lattice. The example given is melting ice cube. Let's look into the samples of vaporization. Vaporization is the changing of a liquid to a gas where it causes vaporization. And this will require energy because the bond between the particles which are close together in the liquid need to be broken. So the particle must also be given enough energy to be separated by considerable distances. So in this example, we have when water is heated to the boiling point, 100 Celsius at sea level, it transitions from liquid to gas, steam, as bubble form throughout the liquid. Heating and cooling curve. Refer to the above graph. When a solid is heated, it first melts into a liquid, and then the liquid vaporizes into a gas. The temperature versus time or energy supply graph for this process has two flat sections. This flat section indicate that during a change of state, the energy absorbed goes into breaking the bond between particles, so there is no temperature increase until the change is complete. Conversely, when a hot gas cools, energy is released as bond formed between particles. This is the reason that steam produces a much worse burn than a small amount of boiling water at the same temperature. That's conclude to this session, and I look forward to seeing you at the next session. Please subscribe to Germ Study Live YouTube channel. Don't forget to turn on notifications so you don't miss any update. Best of luck in your studies and upcoming exam. Wishing you every success. Thank you for your support and cooperation.